Hello scientists, this is Miss R and we're going to do the Unit 6 test review right now. Here are some initial definitions that you're going to need to use. These are some math words. What you mostly need to know here is quotient is the answer you get, is the result when you divide two numbers. So quotient goes with divide. Let's see if you got the rest of them correct. Sum is add, difference is subtract, and product is multiply. This word means how fast something is done. It's one unit divided by another. And the second unit is a unit of time. So for instance, speed in miles per hour or kilometers per hour of these race cars here would be an example of rate. Rate is how fast something is done, and power is a rate in this unit. Power is how fast work gets done. Meter is the unit for displacement. Displacement is how far you've moved something when you're doing work. It's different from distance. Distance is traced across the whole path. Displacement is kind of the bird's eye view of your path. So displacement is measured in meters. Watt is the unit for watt. Light bulbs, of course, are measured in watts. Watt is the unit for power. And light bulbs are measured in watts because that's the amount of electricity it takes to run the light bulb. And electricity can do work, so we measure electricity in watts sometimes. Newton, here's a picture of Isaac Newton. Newton is the unit for what? When Isaac Newton was hit on the head by an apple, he felt a what? Hopefully you guessed force. Newton is the unit for force, which is a push or a pull. It can be electromagnetic between magnets here. It can be friction force, pushing against the friction, or it can be the force of gravity, or it can be you pulling on a pulley. How fast work gets done is a rate, of course, and that particular rate can be measured in horsepower, like this horse here pulling a carriage, or two horses gives you more horsepower. Horsepower is only traditionally now used for engines, and in general, power measures how fast work can get done. How far and what direction an object moves is displacement. Where the object is moving when work is done is the displacement, which is different than the distance. A push or a pull is what Newton felt when the apple fell on his head, and newtons are a measurement for force. A force acts on an object and causes displacement of the object. What is going on? If you've got a force and you've got displacement, F times D is what? Hopefully you remember that one, is work. This baseball player here is doing work. He's applying a force to the ball, and the ball is being displaced. And of course, we talked about how you measure work. It's a force across a displacement. So that's F times D, or right here, force times displacement. So the displacement here on this meter stick that's acting as a lever would be from the fulcrum to the point where you're putting some force, the force due to gravity here. So it would be this displacement, or this distance times this force. What does a simple machine do? Well, do they change the amount of work? Do they change the distance? Do they change the force required? Those are the questions you have to ask about simple machines. Do they keep the total amount of work the same but make the work harder? Why would you want to do that? Keep the total amount of work the same but make the work easier? That sounds like a good deal. Make the total amount of work less? That sounds like a good deal too. Make the total amount of work more. It's B. Keep the total amount of work the same but make the work easier. You increase the distance but you decrease the amount of force necessary to do the same amount of work. Like the screw here, you have to move something along the entire length of all those turns on the screw. So you increase the distance but you decrease the force needed to move something. A screw jack is a great example of this. Work in equals, I kind of just gave it away. Work in equals work out. Like the work being done on this side of the lever, works equals the work being done on this side of the lever. Which simple machine is really an inclined plane? A screw, a crane, a lever, a wheel and an axle, or a pulley? This is a hint here. An inclined plane, if you wrap it around and around like in a parking ramp garage where you're driving around and around in a circle, is really a screw. You're just wrapping the inclined plane in a circle. Mechanical advantage means how many times a simple machine what? Multiplies the input force, multiplies the output force, multiplies the input distance, multiplies the output distance. Think about it. Which side here is going to have the most mechanical advantage? This side is going to have the best mechanical advantage because it multiplies the input force across this distance. You'll have more distance here on this side of the lever, so you're going to have more input force than if you push down here. In the next two slides, which lever has the better mechanical advantage? Do you want to be further away from the fulcrum? Or do you want to be closer to the fulcrum? Further away or closer? And you want to be further away. You want this distance here between the fulcrum and your effort to be big, because if you have a big distance, you need a smaller force. Let's look at which pulley system has a better mechanical advantage. A or B? This is a fixed pulley, which doesn't actually have any mechanical advantage except changing the direction you need to pull. Or A, a movable pulley, which makes you pull twice as far. You have to pull up twice as much rope as the displacement of the object. However, it gives you a 2-to-1 mechanical advantage. So it reduces the force you need in half. So if you're little old me, you can pick up something much heavier if you use this pulley because it has more mechanical advantage. Which of these tools is a wedge? Here's an example of a wedge. It's one that you might use when you're chopping wood and trying to split something open. Split a big piece of wood open into smaller pieces. That's really what splitting wood is. A screwdriver has a wedge on the end of it, which is really just two inclined planes put together. Power is what? Remember, it's a measurement of how fast you can do work. So how fast you do something, what's that called again? Here's an example of two engines, and you can think about how much horsepower each has and how that would relate to how fast you can get a job done. If you want to move your car up a hill, do you want a V6 with lots of horsepower, or do you want a lawnmower engine? Both of them have different amounts of horsepower. Power is the rate at which work is done. So you have a bigger horsepower engine, that'll move your car up the hill. If you have a smaller horsepower engine, that's not going to do as much work as quickly, and it might get your car up the hill, but it's going to do it very slowly. It doesn't have much power. When you use a screwdriver versus an electric screwdriver, the amount of work stays the same. The rate at which work done is different. You can do more work with the screwdriver, you do less. You do the work in less time with the drill, you do less work with the drill. Take a second, pause the video, read these over again, and think about which ones are correct. There's more than one correct answer here. If you guessed A, B, or D, you're absolutely right. The amount of work always stays the same. The rate at which the work is done is different with the electric drill. You have more power, so you can do the work more quickly. Power, remember, is a quotient. You divide something by something else. So it's how much work you can do in a certain amount of time. So work and time. Power is the quotient of work divided by time. The type of simple machine shown in this photo is, of course, a lever. And here's a photo here as well. The resistance end here is the end that you're lifting something on. The fulcrum is the thing in the middle that you're trying to balance something on. The effort force is the end you pull down on with the spring scale. The spring scale looked a little bit different in our lab. What would happen if we move the fulcrum towards the spring scale? In other words, if we move the fulcrum, say, over here to this clay block, where this clay is, that would make the resistance arm greater and the effort arm smaller. And if you're going to make the effort arm smaller, the mechanical advantage is going to decrease and you're going to need more force. If you decrease the distance, that you increase the force. The amount of work done by the effort end of the lever is the same. It's always the same as the resistance end. The moving pulley is the one that moves with the load. So here, the load is attached to the moving pulley, and that pulley is actually going to go up when you pull on this string here. Fixed pulleys are attached to the ceiling, or in this case attached to a rod at the top of the countertop here. They don't move. Moving pulley systems, the force needed to move the pulley is decreased because you do have some mechanical advantage here. And the distance you have to pull the string is increased. When you pull the string up, you have to pull twice as much string as you would with a single fixed pulley system. The fixed pulley system doesn't give you any mechanical advantage, but it does change the direction you have to pull the string. You still have to pull the string the same amount of distance would if you just pulled up the block with the string directly attached to it. All right, that's it. You should be ready to take the test. Good luck. Thanks for watching.